Hello everyone, welcome back to Distributed Generation Smart Grid lecture series. In this video, we are going to discuss about another kind of most popular renewable energy generation system, wind energy conversion system. Wind energy converter or WCS, wind energy conversion systems, which convert wind energy into electrical energy. The principal component of wind energy conversion systems is the wind turbine. And this is coupled to the generator through a multiple ratio gearbox. Usually, induction generators are used in wind energy conversion systems. The main part of wind turbine are the tower, rotor, and nacelle. This nacelle accommodates the transmission mechanisms and the generator. There are many advantages of wind energy systems. It is environment friendly and pollution free. There are potential exists to the harness the wind energy. Such kind of potential is available. Cost of generation decreases over a period of time. Low operation and maintenance cost required. The turbine technologies are matured nowadays. There are recent advancements in the technologies in the development in the turbines. Operation easiness and feasibility of automation. Full automation is possible. And these are efficient and reliable kind of power supply. And these are free and inaccessible source of energy. That is the renewable source of energy. And disadvantages of wind energy systems are, as you all know, that it is greatly depending upon the climatic changes. That is intermittent availability of wind producing a variable energy output. And the low energy density, which requires a large area to obtain a reasonable amount of energy from a wind farm. And high initial startup cost, installation cost is high, even though the cost is reduced as the time progresses. The generation cost is reduced. And noise pollution will be there in case of a wind energy conversion systems. And let's see what are the components of wind energy generating systems. And you can see various components like low speed shaft is here. These are the components I am going to show. High speed shaft with a mechanical brake. Then you can see the hydraulic systems associated with the wind energy conversion system. Then nacelle, I told this nacelle actually accommodates the transmission mechanisms and generators. Then this one is the anemometer. Then this one is the wind vane. Then next part is the cooling unit associated with this. Then you can see electronic controllers in that system. Then yaw mechanism. Then next one is the tower. Then you can see the generators. Usually using induction generators in the wind energy conversion systems. Then gearbox. Then hub, which is known as the hub. Then rotor blades. And these are the various parts of a wind energy conversion system. So as I told that nacelle accommodates the transmission mechanisms and generator. And here you can see that rotor which may have two or more blades associated with it. Then wind turbine captures the kinetic energy of a wind flow through the rotor blades and transfers the energy to the induction generator side through the gearbox. Kinetic energy of wind flow is captured by rotor blades, and this kinetic energy is transformed to the induction generators in order to convert that into electrical energy. The generator shaft is driven by wind turbine to generate the electric power. The function of the gearbox, you can see the gearbox here. Gearbox is to transform the slower rotational speed of the wind turbine to higher rotational speed on the induction generator side, in order to transfer the slower rotational speed of the wind turbine to higher rotational speed. Then output voltage and frequency is maintained within the specified ranges by using supervisory metering, control and protection equipments. That is, the electronic controllers are presented in this diagram as you can see. Then wind turbines may have horizontal axis configuration or a vertical axis configuration, and normally average commercial turbine size of wind energy conversion system was 300 kilowatt until 1990s, but recently many machines of large capacity up to 5 megawatt have been developed and installed in case of in a wind energy conversion system. And you can see a anemometer here is a device for measuring the wind speed and direction. In order to measure the wind speed and direction, we are using anemometer here, and you can see a wind vane used here. It is an instrument used for showing the direction of wind. Again, this is this wind vane is a device that measure the direction of flow of wind. Sometimes it is known as weather vane. And these are the main part of the wind energy conversion systems. And these are the power output equations of a wind turbine, which is determined by several factors such as wind velocity, size, and shape of the turbine. The power developed is given by P, which is equal to half Cp rho V cube into A. P wind velocity is PV, which is half rho A V cube in watts. And where P V is the power, wind power, you can see that wind power output of wind turbine is here it is denoted as PWT, wind turbine power output of the wind turbine, that is half rho AV cube into Cp, which is in watts. Power in the wind speed is given as PV here in the first equation, that is half rho AV cube. No term Cp is there, that is coefficient of power. And when you are multiplying with the coefficient of power coefficient, we will get power output of the wind turbine, and that is multiplied with the efficiency, will get the power output of wind energy generator, that is Pg, that is PWT into eta in watts. And you can see that that power wind turbine where you can see that equation is half rho AV cube into Cp, where P that is the wind power output. Cp is known as power coefficient. Rho is the air density, that is usually expressed in kilogram per meter cube, and V is the wind velocity in meter per second, and A A is a swept area of a rotor blade in meter square. Swept area of rotor blade in meter square. And this is that particular equation I already shown. And power coefficient Cp, you can see that is a measure of is a function of lambda and beta. So power coefficient Cp actually gives a measure of amount of energy extracted by the turbine rotor. Its value varies with rotor design and tip speed ratio, or TSR, and the lambda is actually the representation of tip speed ratio. This tip speed ratio, or lambda, is the relative speed of rotor and wind, and has a maximum practical value is about 0.4. The maximum practical value is 0.4. And the torque output often suffers from dynamic variation due to the fluctuations in wind speed caused by climatic conditions like tower shadow, wind shear, and turbulence. So these variation leads to a dynamic perturbation in the output power, and hence a flicker in the generated voltage will be presented in the power output generated from the wind energy conversion systems. So in a constant speed wind turbine, power variation and voltage flicker do pose a problem in the network. So, but in the contrary, when you are using a variable speed wind turbine systems, which provide much smoother output voltage and more stable bus voltage with lower losses is achieved. However, the major problems of wind energy conversion system is that due to the intermittent nature of generation and energy consumption in the generating plant itself, the effective or declared net capacity is lesser than the nameplate capacity of any wind energy conversion systems. These are the various configurations of wind energy generators that typically you can classify it as a constant speed wind turbine and a variable speed wind turbine. And this constant speed wind turbines operate at almost constant speed as predetermined by the generator design and gearbox ratio. The control schemes are always aimed to maximizing either the energy capture by controlling the rotor torque or the power output at the high wind by regulating the pitch angle. In order to, that is known as pitch angle control, in order to tap the maximum power from the wind turbine. And according to the control strategy, constant speed wind turbines, again you can subdivide it like a stall regulated turbines and pitch regulated turbine. This constant speed wind turbines have many advantages, also disadvantages associated with this. And constant speed stall regulated turbines have no options for any control input. Here the turbine blades are designed with a fixed pitch angle to operate near the optimal tip speed ratio for a given wind speed. Consequently, this results in the reduced rotor efficiency and limitations in the power output. Some other variations of this concept is to operate wind turbine at two distinct constant speeds by either changing the number of poles of the induction motor or changing the gear ratio. The commonly used type of wind turbine is a pitch angle regulated turbines. Here you can vary the pitch angle to tap the maximum power from the wind turbine. These constant wind turbines operating systems which have following advantages. They have simple, robust construction and are electrically efficient. Then they are highly reliable due to fewer parts. No current harmonics are generated as there is no frequency conversion in a constant speed wind turbines. They have lower capital cost as compared to the variable speed wind turbines. However, they have following disadvantages as compared to the variable speed turbines. They are aerodynamically less efficient, and they are prone to mechanical stress and are more noisy. And let's see what are variable speed wind turbine systems. A typical variable speed pitch regulated wind turbine system, you can see it from this diagram. It has two methods of controlling the turbine operation via speed changes and blade pitch changes. The control strategy usually employed are power optimization strategy and the power limitation strategy. So the power optimization strategy is employed when the wind speed is below the rated value. This strategy optimizes the energy capture by maintaining a constant speed corresponding to the optimum value of tip speed ratio. If, however, speed is changed due to the load variation, the generator may overloaded for wind speed above the nominal value. In order to avoid this, methods like generator torque controls are used to control the speed. And in case of a power limitation strategy, which are used for wind speed above the rated value. This strategy limits the output power to a rated value by changing the blade pitch to reduce the which will leads the reduction in the aerodynamic efficiency. So you can see the control this wind energy conversion system with its control strategy here. Pitch mechanism, the wind turbine, then gearbox mechanism, induction generators, and the power output is compared with the reference power, and accordingly torque controller will operate, and reference power is generated. That command is dynamically changed with respect to the information from the pitch mechanism and the pitch controllers. So this is a closed loop speed control mechanism for wind energy conversion systems. And the variable speed wind turbine have following advantages. They have high energy capture capacity and are subjected to less mechanical stresses, and they are aerodynamically efficient and have low transient torque. Then no mechanical damping systems are required, as electrical systems can effectively provide the damping. They do not suffer from synchronization problems or voltage sag due to stiff electrical controls. And compared with the constant speed wind speed turbines, they have following disadvantages, that are they have lower electrical efficiency. Aerodynamical efficiency is less in the constant speed turbine, but here lower electrical efficiency, and they are more expensive and sometimes requires complex control strategies in order to tap the maximum power. We need a control strategy, and also we cannot fix the voltage and frequency levels. We need more complex control strategies.